Hello, and welcome to this video on hypothesis testing. This is a new subject and it has a lot of new parts, so it'll be a long video and there'll be new things introduced along the way, and hopefully by the end we'll be able to tie them all together. But when we say hypothesis testing for us, what we're going to be doing is testing to determine if we think the mean of a population has changed. So that means that possibly we have some data from a population. Okay, so maybe a population average has been given and been accepted over time, but what we're going to do is we have a sample that may be different, but since all samples can vary, we're going to see if it means that we believe that the population average has actually changed. Okay. And it's important to note that when comparing a population average to a sample average, a couple of things can really make a big difference. The sample size can have a big influence on how closely they're related, the standard deviation, and when we go to do our hypothesis testing, there's going to be a level of significance, a threshold, if you will, as far as what we accept to be a difference between the two. So, in hypothesis testing, one thing we're going to have to do is come up with a null hypothesis. This is our general hypothesis, and this is really easy to do. Here's an example word problem. It says, a certain breed of bird usually spends its summer in North Carolina. Studies have shown that the birds usually spend 80 days in North Carolina with a standard deviation of 12 days. Dave decides to track 10 of these birds and finds that his sample spent an average of 70 days in the state. And 70 is very different than 80, but it's not a very large sample, 10 here. So we're going to see what that means. But as far as staying the null hypothesis, that would be our population data that has been given, and usually what has been accepted. So down here is the notation for a null hypothesis. H sub 0 stands for the null hypothesis, and of course the mu here, what looks like the U, is a population mean. So the null hypothesis is that the population mean is 80 days. Okay. Now an alternate hypothesis would be something different than the null. And I give a couple examples here, but it's worth noting that you would only have one alternate. So basically the null hypothesis is what we go with, or the alternate. So there's only one alternate, but it could come in 3 different versions. And the notation is H sub 1. So the H sub 0 is the null hypothesis, which talks about the given data for the population mean. And the H sub 1 is the alternate hypothesis, which is what we think it may have changed to. So we could have a less than the value which you see here, the mean is less than 80, or greater than, or we could have a third option which is neither, it's not 80. Okay, and over here I've got listed left tail, right tail, two tail. This is going to be important because we're going to compare these things using z-scores. And you may remember that if you're talking about less than a number, you did a left tail test on the z-score, which meant you got your number from the z-score table. If you had a greater than, you had subtracted by 1. But we're also going to have a two-tail, and I'll explain that in the last example when we get to it. Okay, so here's the problem again. I did add to the end of it. It says Dave wants to test to see if the average is now less than 80 days. And he will use a level of significance of, and here's a symbol alpha, which stands for level of significance for us, 0.05, which is basically 5% if you think about probability. So based off of the less than 80 days, you can see our alternate hypothesis, and it's going to be a left tail. Here's that level of significance stated, but some things that are useful when calculating z-scores, as we're going to be doing here in a moment. Sample size of 10, population standard deviation of 12, and a sample average of 70. Okay. So we're going to get what is called a p-value, and this is kind of the similar to the probability that comes from a z-score. Okay, but we're going to get that from first calculating the z-score. And since in this case the sample size is going to matter, because the larger the sample, the more certain we are of this sample mean, you may see this z-score formula is a little bit different than when we first introduced it, because you see the square root of n on the bottom here. So it is a little bit different than the first z-score formula that we introduced. Okay. But we're going to plug everything in, and here we go. So z of 70 with everything plugged in here gives me negative 2.64. I look that up in the z-score table, and I get a probability of 0.0041. Now, the probability in this case, since it was a left tail test, is that number. So when I get the actual probability for the tail that I want, that'll be my p-value. So in this case, if you have a left tail test, it's always going to be the same as the probability you get from the table. So let's talk about what this means a little bit. First of all, the p-value is the level of significance, and it's less than, the p-value is less than the level of significance. Another way to see this is an inequality here, comparing our two values. So the level of significance of 0.05 means that we can view the data as significant if there is less than a 5% chance that the sample mean could occur. So basically, how far away from the population mean are we, and how likely is it that we could be there? Okay, so we're accepting up to 5%. Okay, the p-value here says that 0.0041, which is 0.41%, means that there's a very small chance that we could be over here at 70. Okay, so if you think about the normal distribution curve, this chance puts you very far at the end, especially on the left tail. Okay. Next slide. Okay. So because the p-value there that was 0.0041 is less than the level of significance, the 0.05, we conclude that 70 is so far away from 80 that we think the mean has changed. Meaning it's very unlikely that a sample would have given us a mean of 70 if the actual mean is still 80. Okay. So, in conclusion, what this means is we reject the null hypothesis, okay, meaning we don't think that it's 80 anymore. And that comes from our level of significance and our testing. Okay. And by default, that means that we believe that the alternate hypothesis is true. Okay, we believe that the average is now less than 80. But with statistics here, we didn't actually prove anything. The only way to prove that the population average is less than 80 would be to go through the population again. But comparing it to a sample, we believe that the population is now less than 80. And after you have a p-value, it's very easy to conclude your test. Basically, if your p-value is less than your level of significance, you'll reject the null hypothesis. If your p-value is more than the level of significance, we say you fail to reject the null hypothesis. We never really say accept or prove or disprove, okay? Because there is a chance that our sample is really bad and really means nothing at all in terms of our data. So it's just really important to note that we can't say that the null hypothesis is false. We just say we reject it and we believe the data has changed. And we also don't say that we necessarily accept the alternate hypothesis in that situation. It just means that we believe it to be true so that we might use it for other data, but we haven't necessarily proved either way. Because we could change our level of significance, and that could change everything. So here's a second example, and this is going to be a right tail test, so pay attention there. It says bacteria A has been known to die after 30 hours with a standard deviation of 2 hours. Tim takes a sample of 20 bacteria and calculates the average lifespan to be 31 hours. Tim wants to test if the lifespan of the bacteria is more than 30 hours using a level of significance of 0.01, so basically 1% here. So since it wants to be more than 30, that's going to be a right tail test, and here's our alternate hypothesis, and here's all the other information we got from there. Plugging this in and doing our z-score, we get 2.24, which if we look 2.24 up in the z-score table, we get probability of 0.9875, but that's to the left. The z-score table always gives us the amount or the probability to the left. So if we have a right tail test, we want the probability of landing to the right of 31. Okay? So this is the chance of landing to the left of 31. We're looking for landing to the right of 31 since our alternate is greater than 31. So we'd subtract that from 1, so the chance of landing to the right of 31 is 0.0125, and that's our p-value. Our p-value is greater than the level of significance, so we fail to reject the null hypothesis, which means we still believe the lifespan is 30 hours. Example 3, we'll go through a two-tail test. So here, at the manufacturing date, Jeeps have a average of 17 miles per gallon with a standard deviation of 2.5. A test 6 months later on 10 Jeeps found a sample average of 15 miles per gallon. So you may think that you want to test to see if it's less than 17, but sometimes you just want to see if things have changed within a certain level of significance. And the question here is, does the sample suggest that the average is different from 17 miles per gallon? And we're going to use a level of significance of 10% of or 0.1. So here's our null and our alternate. So notice our alternate is not 17, which is going to be a two-tail test, which basically means we could be on either side of 17. Okay, we could be below or above. And here's all the data that is in the problem. So we go through, we get a z-score of negative 2.53, which when we look up in the table gives us 0.0057, which is to the left. So in this case, since it's a two-tail test, we know that there is 0.0057 the probability of being to the left of 15 is 0.0057. But we're going to double that because we're curious about being the same distance to the right of that. So when we say not equal to, that includes the left and the right. So we're measuring the probability of being that far away in either direction. So basically I took this number and doubled it to get a p-value of 0.0114. So basically that means to the left of 15 or to the right of 19, since the sample mean and the population mean are 2 apart. But the p is less than the alpha or level of significance that we were given, which means we reject the null hypothesis. So once again, you can see that the size of the level of significance would make a difference for our test. Okay, so if this was still 1% or 0.01, we would have got a different outcome. So that will change from problem to problem. And also change with the data given. So be very careful. Okay. The last thing to mention here is in the last section of the chapter, they do hypothesis testing using proportions. We could go through everything here, all 14 slides again, but everything will be the same except for how you calculate the z-score. You may recognize some of this from previous chapters, but here's the sample probability or proportion, the p-hat, and the population probability is p. Of course, q is the failure rate, and n is the sample size. So if you got the z-score here, you would still have the same work to do with a left tail, right tail, or two-tail test, and you'd be comparing that to a level of significance. So everything would work out the same, and you would conclude the same way by comparing the p-value you get to the level of significance.